I'm going to come back about this B. You remember in the previous 3 examples, we look at the 3 phenomena. And one, you get the little friction, you have a attenuating oscillation in example 3. The example 5, and you really get all the exponential function. And what else? And the example 4, we really have a different phenomenon. It's, we call it critical damping. So let's back into the quadratic equation, which is mr squared plus br plus k equals 0. And if you remember in the college algebra or just high school algebra, any quadratic equation have 3 different cases. Depends on this delta, we call it discriminant, which equal b squared minus 4mk. In your formula, maybe you call it b squared minus 4ac. That's the same thing. My a equal m, c equal k. So depends on if the delta is bigger than 0 and or less than 0, or in this case equal than 0, you're going to get different solutions. Let's start from the easy one. When the delta bigger than 0. Now the delta bigger than 0, in this case, look at the delta. That's example 5. Delta equal 5 squared minus 4 times negative 6 equals 25 plus 24 equal 49. That delta gives you 2 pieces of information. First, you can factor it out as a real number. Second, that's a 7 squared. You got all nice integers. And how about the example 3? Example 3 is this, is r squared plus 6r plus 25 equals 0. And then your delta, in this case, let me show you, you may forget, that's the example 3. Can you see it? It's the attenuating oscillation. So delta equals 6 squared minus 4 times 25. It's 36 minus 100, which is negative. That's what matters. If it's negative, how are you going to solve that? Let me try to solve it. You get the imaginary solution. If I want to solve it, I have the r squared. How about write it into a complete square? Then have 3 squared equals negative 25 minus plus 3 squared plus 9. So I have the r plus 3 squared equals negative 16. Then r plus 3. You see a complete square cannot be negative. What you do? You have the imaginary. Then your r equals 3 plus minus 4i. And now your solution will look like this. And the C3 plus C4 let me put it this way, consistent. That will be 3 minus 4i, this. Then say, wait a moment, that's not right. It's not what I need. and what I want, it doesn't make sense. Does not make sense. Why? I will know this is my solution. So how do you coincide to confirm this solution to that imaginary? Well, the answer is here, the Euler formula. You know, all you need to remember is the Euler formula, e to the 4it equal cosine 4t plus I sine 4t. And that's where you get the trig function. Well, we're not going to go all the detail, but you just remember this is equivalent to e to the negative 3t times c1 cosine 4t plus c2 sine 4t. It looks exactly what we had here. Actually, yeah. See, C1 of this and the C2 of that. Okay. So the last one, the example 4, if you remember, you are talking about this equation. Let me show you back and forth. Is this equation. Your m equal 1, b equal 10, k equal 25. Then you get this r squared plus 10r plus 25 equals 0. So what's your delta? Your delta is 10 squared minus 4 times 25 equals 0. And then what you get is r plus 5 squared equals 0. You miss one solution. You only get the r1 equal r2 equal negative 5 for that example 4. So what you have, now let's go back to what you see here. You really need 2, but you only got so far one solution. So the example I showed you, hey, you have another one. All you need is multiply t, get the e to the negative 5t. If you give me twice of that, that does not count. That's called linear dependent. That's not a count. It's the same as this. You remember you're going to put a C1, C2 anyway. So the next one is multiply t. Put it here. So that's the critical damping. And our solution, you see, kind of like overdamping. You just have a decaying curve.